Okay, so today we're looking at another application, and this time it's rectilinear motion. So specifically, we're looking at motion in a straight line. Okay, this is going to be called rectilinear motion, and the idea is that you can use rectilinear motion to model the motion of a falling object. Okay, you can look at a vehicle moving in a constant direction. Okay, so that's going to be a car or an airplane, whatever the case is. Um, you could also look at a particle in motion, or also electromagnetic waves. Okay, if you're looking at the wave as a whole, it's going to be traveling in rectilinear motion. So specifically for this topic, we will be looking at two things. We're going to be looking at displacement, okay, and we're going to be looking at distance traveled. So we'll look at defining those two in a moment, okay, but we should all understand that when we're looking at movement in a straight line, okay, by convention we're saying that movement from left to right, okay, this is going to be positive motion, and movement from right to left, okay, this is going to be considered negative motion. And similarly, if you are moving upwards, okay, that's considered to be positive. And if you are moving down, that's going to be considered negative. Okay, so now let's take a look at displacement versus distance. Okay, so here we have our two concepts. We have displacement versus distance. And for displacement, first of all, you're looking at the length of a path specifically from the start of the movement to its final position. Okay, so we're looking at starting at, let's say, time t equal to t1, and we're going until time t equal to t2. Okay, and we want to know what's the length of the path from the start of the movement to the final position. So let's suppose that we're looking at this, and we have rectilinear motion. Maybe we are starting off with an initial displacement of 0, okay, and we're going to have an object moving from left to right, and let's suppose that it travels 4 meters to the right, okay, fine. However, what if it then sort of stops, turns around, and it's going to travel 3 meters back in the negative direction? We want to look at displacement for this object. Okay, so right now we would have displacement is going to be the difference between the starting displacement and the final displacement. So here we're looking at its final position is going to be 1 meter, and let's actually just call that S of T2. Okay, that's going to be its final position. We're going to subtract from that its starting position, which would be S of T1. And what that's going to give us is essentially we stopped, S of T2 was 1, S of T1 was 0, and we end up with our displacement for this motion being just 1 meter. Okay, so that's sort of a brief introduction to displacement. Now let's take a look at distance. So for distance, we are looking at the total length of the path covered from T1 to T2. Okay, so here, let's suppose that we have the same sort of motion. So we're going to be starting off at 0. We're going to be moving to the right by 4, and then we're going to be moving back by 1. So this time what we want to look at is the total length of the path. And so our distance is not going to be 1 meter. Okay? We'll notice that initially we traveled 4 meters in the positive direction. We want the total length, so that's going to be 4 meters, plus we're going to add in that we traveled 3 meters. And it does not matter that we traveled 3 meters towards the left in the negative direction. The total distance here is just going to be essentially the absolute value. So it's all going to be considered positive. We have 4 plus 3. It's just going to be equal to 7 meters. So for this example, we have that if this was our motion, our displacement would be 1 meter, but the distance, okay, the total distance traveled in this case is going to be actually 7 meters. Okay, now let's take a look at a little bit more of the notation and a little bit of a more in-depth calculus definition for these concepts. So how can we end up calculating displacement of an object from time t equals t1 to time t equal to t2? Well, really, you don't absolutely need calculus to do this. Okay, there are going to be two ways we're going to look at, and the first way without calculus, you could simply just do what we did before. You could take your final position minus your initial position, so s of t2 minus s of t1, and that's going to give you your displacement. Okay, so that's the one way how to do it without calculus. Now let's take a look at how to do it with calculus. So with calculus, what we're going to do in the initial setup is going to be a little bit more complicated, but in the end we'll end up with a very nice formula for calculating displacement. We're going to start off here with the graph of our object's velocity. So if this is the graph that we have, let's just sort of zoom in here for a moment. So this graph is going to represent the velocity of our object as time goes by. So here you can see that our velocity is positive. We reach sort of our maximum velocity right at this point, and then we're sort of slowing down, and the object actually at this point would be having zero velocity. It wouldn't be moving at all. And then if it has negative velocity, that means it's actually traveling backwards. It's traveling in the negative direction. Okay, so that's sort of the initial setup if we look at its graph and understand it in that way. What we're also going to want to do, though, is try to use this graph to calculate the displacement. Okay, so we want to know what's going to be the difference between the final position and the initial position. So one way of doing this is that we can actually look at it and try to approximate it. And this is actually very similar to what we've done with many of our other applications. We want to figure out a way of approximating displacement, and then we could figure out a way of improving the accuracy of our approximation, and then figure out a way using limits to bridge the gap between our approximation and the exact value. So in this case, this is going to be a very familiar concept. If I want to approximate the actual displacement of my object, what I can do is divide the motion of our object, in this case from time t equal to 0 to time t equal to 5, into different lengths of time, into different sub-intervals. In this case, just to keep it easy, let's use 5 different intervals, which means each interval is going to have a base width of 1 second. So really we have delta t is going to be equal to 1. Okay, and let's suppose our units are seconds. Then what I can do is further assume that on each of those sub-intervals, so right here, if this is going to be delta t, I can assume that the velocity is constant. So if I'm going to go up to this point, okay, and really what I'm going to do is assume velocity is constant, which means that we end up getting that the displacement on that one interval of time is just going to be the 1 second multiplied by the velocity at this point right there. Okay, and that's actually going to give us the area of this rectangle. I could do the same thing here at time t equal to 2. I'm going to assume that our velocity is constant, and I'm going to take the velocity at that interval in time and multiply it by the base width, again multiplied by delta t. I can go here to 3 seconds, and again, if I assume that the velocity is constant, then I could say this is going to be the total displacement on that time interval, and do it one more time here. You'll notice at 4, if that's exactly where I cross over, then the height would be 0, and so the actual assumed approximation in displacement would be 0. If I go over here to 5, I'm going to get a negative velocity, and so my rectangle will be below the curve. This is actually going to be area that would end up being subtracted. Okay, and again, this is really just a Riemann sum. What we have said here is that the actual displacement can be approximated by adding up from 1 to n. In this case, n would be 5, but I'm just going to say from 1 to n, we're adding up the areas of all of these rectangles. Each one is going to be just the height of our function. Okay, that's our assumed constant velocity, multiplied here by the change in time, which would just be delta t. Okay, and so really this. What do I want to do with it? I want to increase the accuracy of this approximation. To do so, obviously, I'm just going to use more than 5 different points in time, more than 5 different subintervals, more than 5 different rectangles. And the more we use, the better the approximation gets. So if we want to find an exact formula to calculate displacement with, well, all that we're going to do now is the limit as the number of points, the number of sample points here goes to infinity. We're going to end up adding up all of those. So that's from 1 to n. And we're doing v of ti times delta t. What is this? Well, this is precisely going to be our definition of the definite integral. So what we end up with is that it's going to be given by the integral from t1 to t2. In our case, that would be from 1 to 5. So from t1 to t2. And what are we integrating? Well, we're integrating here our velocity function, so that's going to be v of t dt. So if you want to calculate the displacement, this right here, this is going to be very much the formula that we end up using. So now we have 2 different ways to define our displacement. We can do so without using calculus. So really here, we said we can take the final position and we can subtract the initial position. That's going to give us our displacement. And we could also use calculus. We could use a limit and essentially a Riemann sum to calculate displacement using a definite integral. So maybe you've already put these 2 things together, but what you end up getting then is a very nice, very intuitive explanation of how the fundamental theorem of calculus part 2 works. Okay, we know from FDC2 that if I'm going to be doing an integral from t1 to t2, and in this case I'm integrating my velocity function, I can calculate this by finding an antiderivative of my velocity function, plugging in my upper limit of integration and subtracting my lower limit of integration. And that is precisely what we have here. We have s of t2 minus s of t1. And really we have that our displacement function, s of t, is an antiderivative of our velocity function. And so FDC2 gives us that if you want to evaluate this definite integral, we could simply just find our antiderivative, find our displacement function, and take the difference between those 2 values. Okay, so this is one of the main things that we're going to be taking away from this section, okay, is understanding how FDC2 works with displacement and how it connects the velocity function in a definite integral to its displacement function. Now, in the next part, we're going to look at a few definitions relating position function, a velocity function, and an acceleration function in terms of displacement and distance traveled. So here we have position, velocity, displacement, and distance. The first thing we're going to look at is the position function. And we remember from Cal 1, okay, that if you do the derivative of your position function, you're going to end up with displacement. And so what that means is that if you do the antiderivative of velocity, okay, you're going to end up with your position function. Okay. Also, looking at the velocity function, we remember that the derivative of velocity is going to give us acceleration, and so here your velocity is going to be an antiderivative of acceleration. Fine. So if we also look at displacement, we remember that displacement here is defined as the definite integral of velocity from time t1 to time t2, and that is just done using FDC2. Really, you could also view it as the difference between your 2 displacements, okay? Essentially the difference between your final position and your starting position. And then the last thing we're looking at is the distance traveled. Okay, so the distance traveled will be the integral of speed. It will be the integral of your absolute value of the velocity function. And we remember from Cal 1 that we are comfortable dealing with absolute value functions as a piecewise function, meaning that we can drop the absolute value if we know that the function is going to be positive, then we know that we can drop the absolute value without changing the function at all. However, if the velocity function is going to be negative, then we're going to drop the absolute value and introduce a second negative to ensure that the velocity there is considered as positive. Okay, so that's going to be how we deal with the absolute value function. So now that we have these definitions, let's actually go and do an example.